Good. Then let's continue. Before we continue now really with the GLM, after introducing the foundations that we need, is there anything that you want to ask with respect to the contents of the morning sessions? I appreciate that they are kind of foundational theory, but there is just no way around them. Doesn't make sense to talk about the GLM and design matrices and beta parameters, or the betas as they are called in fMRI, without talking about matrices. Okay, good. Then let's now talk about the GLM. And this afternoon session is then about the GLM in general, and tomorrow morning we will start then with the GLM for fMRI. And the GLM in general is, of course, a very important probabilistic model in data analysis, because it's the unification of all the things that you know from your undergrad statistics, as I already mentioned. Maybe in the beginning it will look to you most like a multiple linear regression. It has, of course, it's derives from that if you want, but also all these categorical designs like t-tests, ANOVA with interactions and so on, they all are special cases of the GLM. And that's always the nice thing in terms of doing data analysis or modeling data. If you have a model that unifies a lot of things, then your life gets a lot easier and you see many more connections between things than if everything exists kind of in parallel and you have the feeling that things might be connected. For example, simple linear regression and t-test, because somehow both need the Gaussian or can use the Gaussian, but somehow it's not really spelled out what the connections are. So that's what the GLM is good for. And of course, the GLM existed a long time before fMRI. But in the early days of fMRI, or let's say in the 90s in fMRI, applying the GLM to fMRI data was kind of the big research question, and has led to kind of this focus of the functional neuroimaging field on GLM methods until, let's say, 2005, when John Dillon Haynes and other people then used the classifier, which of course people could have used already in the early 90s, because of course classifiers were available there. It took 15 years for people to realize, oh, we can also classify. And since then, I think a lot of people use classification and do classification, so predictive modeling, because it's easier to understand. I don't know. But yeah, it has, I feel actually at this point, maybe as many people are doing GLM analysis as classification analysis, maybe even more classification analysis. These two things are, so one could do, of course, a course on this dissimilarities and similarities of what people now call encoding and decoding models, which is weird. One could talk a long time about it. So they are very similar in many things. Usually, if you start basic classifying things and so on, you shy away from thinking about real or sensible analytical means of quantifying uncertainty. So that's where they fall a little bit short, but then they are more intuitive and of course more approachable, or more, maybe even more exciting if you say we decode what's in the brain, rather than say we model what's in the brain. But of course, you can also use the result of a GLM analysis of fMRI data for decoding, and you can also have multivariate GLMs. So they are very tightly connected, and whether you start to properly understand the methods from the encoding modeling GLM part or from the decoding part, at one point these two things meet if you dig deep enough. Anyway, so we're doing the GLM for general purposes now, and that also then of course relates to everything that you know about frequentist or Bayesian statistic, doesn't really matter. So it's kind of a refresher in classical, or let's say not classical, in linear statistics then. So let's see, there we go. Again, it's useful to have some prior knowledge before one goes into studying the GLM. In typical German psychology, statistic textbooks, you find the Allgemeine Lineare Modell somewhere on page 600, and it doesn't really take center stage there, which is a pity because it would make life so much easier if you introduce it earlier, which is of course what we do. But it also requires a little bit of previous knowledge. So of course it helps to know what expectation covariance are, what statistical models are, how frequentist inference works in general. So what's the basic assumption about how frequentism works. We will, of course, discuss the estimation of the GLM after we formulated it. And of course, these are then special cases of ordinary least squares estimation or maximum likelihood estimation, at least for the beta parameters. So it makes sense to know what maximum likelihood is. And then if we talk about the evaluation, where we, of course, focus on T contrast, because that's, if you do fMRI, that's the first thing that you want to know. Does my condition evoke more, or do I get visual activation or auditory cortex activation if I contrast the auditory condition with the baseline condition or something like that? And this, of course, all works via these kind of contrast 1 - 1 contrast things. They work based on T statistics, and there, of course, it helps to remember what the idea of T statistics and hypothesis testing in general are. We will also introduce them, of course, but we can, again, only do so much. So again, these are things that actually form part of the first term psychology courses here. As I said, the second term then basically starts where we started this morning. After correlation and regression, we then introduce the GLM. And once we know the GLM, then we discuss the specific cases like ANOVA, ANCOVA, and so on in more detail, because then it's a lot easier. Good. So that's what's helpful to have in the back of your mind. And we will now go over model formulation. So we will first write down the model, and then we will look at how we can in general estimate of the model and how we can evaluate them. The examples that I'm using today are essentially the one sample t-test design and simple linear regression. So things that you know, and I think also come up a lot in actual data analysis. And the example, of course, then tomorrow will be the analysis of fMRI data. Good. So the GLM. That's the GLM here. Y equals x beta plus epsilon. That's actually the way it's written in neuroimaging. So there are different ways to write the GLM, of course, in terms of the letters that one is using. That's the standard way how it's done in neuroimaging. And we now look at what these things are. So Y, that thing here is an n-dimensional observable random vector referred to as data. So that's the data. And of course, we are now formulating a model for data. And n-dimensional observable random vector means that we have n numbers. So we have a matrix with a single column. So we have n numbers in a long column. And that then can be a lot of things. So it can be, let's say, if it's 12 data points, can be the heights of 12 people that we measured. If we're talking about fMRI, it will be, but we will look into that in detail tomorrow. It will be the voxel MRI time course of a single voxel. So the GLM in fMRI is applied to each voxel individually. That's the mass univariate approach, which we will discuss in length tomorrow. But anything where you have n data points can be modeled here. Let's keep it at that for this time point, for this time in the course. And I'm saying here that it's random, although that's not quite clear from here, the definition. It's random because this epsilon here is random, and we add something deterministic to it. And of course, one can formally show that if you add something deterministic to a random vector, you get another random vector. Yeah, we are not really going that foundational. So it's random. So if you formulate a GLM on your computer, you can sample that GLM many times, as often as you like. Of course, and that's something that I hope is in all of your heads already, if you have observed real data, so on your computer or wherever in the cloud, this data is conceived as one of the many realizations that you can get as from such a model. Yeah, so that's you can view it from a frequentist perspective, holds also if you do it from a Bayesian perspective, but that's very important. Yeah, so this is a probabilistic model that describes the distribution over data. What you have, your experimental data, is one of the infinitely many realizations that you could get. So that's Y, and Y will always be the data now. X is the design matrix, which is something that we already saw this morning. So these black and white pictures that you see in SPM always, which look like Western blots or whatever. These are matrices, design matrices, and they are and will always be n times p matrices. N is, again, the number of data points. P is the number of columns of the design matrix and also corresponds to the number of parameters. In the design matrix, you encode your experimental design, or let's say the specific model that you use this for. So if you use the GLM as a t-test, then your design matrix looks different as compared if you use the GLM for simple linear regression or for multiple linear regression in fMRI. So the X really depends. And we will look at examples for X today for one sample t-test and for simple linear regression, as I said. Beta is, and X is always known here, so that's important. So X is known, you know your experimental design, you know what kind of analysis you want to do, and it's also not a random entity. Yeah? So we're not talking about correlation here. This is not a realization of something. It's just a matrix that you know because you did your experiment or the whole setup in a specific way. Beta, which is multiplied in matrix multiplication here with X, is an unknown weight parameter vector. It's also called beta parameter vector. And it's p-dimensional, so it's p numbers. And what it will encode is, of course, the weight by which you scale the columns of this design matrix. If you multiply this n times p matrix with p times 1 vector, what do you get? In terms of a vector, a matrix size? What's the size of x times beta?
N into 1, n by 1.
Yeah, exactly, n by 1. So that's a vector then. An n-dimensional vector, which of course makes sense because somehow, or yeah, you add something to that, but somehow you need to get to an n-dimensional vector. So that's n times 1 here. And to this n times 1 vector, you add another n times 1 vector, so an n-dimensional vector, namely this epsilon here, which is a random vector and is referred to as error. And for this error, it's assumed here until further notice, namely tomorrow if we talk about covariance components, until further notice, it's distributed according to a multivariate Gaussian, an n-dimensional Gaussian, with expectation parameter 0n, so that's this n-dimensional vector of all zeros, and with a covariance matrix given by sigma square, a scalar larger than 0, times the identity, the n times n identity matrix. And what's unknown here is this variance parameter. So that's the GLM, and of course that's the GLM in general form, and of course it helps to look at examples. But yeah, before we do that, some things I think are worth mentioning. So if you look at a single component of this y, then of course you can write out what, so for example, if you're in the ith row of y, of course there's also an ith row of this vector, which you get by multiplying the ith row of the design matrix with the beta parameters. So that's this xi1 beta 1 plus xi2 beta 2 to xip beta p. For those who have seen multiple linear regression, this of course looks fairly similar to multiple linear regression. Your x would be what you called independent variable, and your y would be your dependent variable. That's the case here, of course, also in general. So you can view x beta, or at least x. You can view as the independent variable, and y as the dependent variable. But that's kind of psychology talk, and you get into the problems of talking about what is the variable, what is a vector, and what do I mean by variable, and so on. So if you have this connotation or this idea of independent and dependent variables in your head, yeah, you can map them onto x and y, but it gets tricky, so it makes sense to use the proper terms. But of course, the x's you know, and you want to, you measure the y's, and you somehow want to relate the x's to the y's, and you do this via the betas. So the beta here, as you can also see, they quantify how much each column of the design matrix contributes to y. But you also have this error term here, this epsilon I, and this epsilon I is of course one component of this epsilon vector, namely the ith component. And because it has, the epsilon vector has the spherical covariance matrix, all the epsilon i's, these n epsilon i's, they are independent, and they are all distributed according to a univariate Gaussian with this variance parameter sigma square. So that was the stuff that we did just before the lunch break. And yeah, so that's what you see. So each data point is essentially, each data point yi under this model is conceived as resulting from scaling values in the columns of the design matrix by beta parameters and adding a Gaussian error term to that. And the Gaussian error term is here motivated, of course, in terms of the central limit theorem, which says that if you have many random things that all have their specific distributions, if you add them all up, you get something Gaussian. And that's also the logic behind this model. This is everything, this is kind of, if you want, unexplained variance, and this is your explanation for the variance in the data. Yeah, so here in the data somehow goes up and down, and you explain that based on some theory, which you encode in x beta, which is deterministic. And you say, okay, but my theory is not perfect. There are many things that I don't explain with my theory. If I assume there are really many things and they all also contribute, then they add up to be Gaussian. And this is how the Gaussian is motivated. There's always then also in undergraduate psychology, there's always then the confusion between normally distributed errors and normally distributed data. And there doesn't need to be any confusion actually. So the errors are assumed to be normally distributed, so Gaussian distributed, and assumed to be centered on 0. From this, it follows, namely by means of our linear affine transformation theorem, that the data are also normally distributed. And how exactly, that's what we look at here. There's a typo. This should be sigma squared times in. put an IN behind that, please. So if we have this model here, y equals x beta plus epsilon, where epsilon is this multivariate vector centered on 0 and spherical covariance matrix sigma square IN. If this is our model, then from the specification, it follows that the data vector y is distributed according to a multivariate Gaussian with expectation parameter corresponding to this vector x beta and covariance matrix sigma square IN. Why? Well, if you believe what I told you about the linear affine transformation theorem, we have here this epsilon vector, which is like our x earlier on, which is multivariate normally distributed with these parameters. Again, there's this IN listening, it should read like that. And our y is a linear affine transformation of epsilon, where our matrix R that we saw earlier is just the identity matrix. And then we add something to it, namely this vector x beta. That's our B from earlier on. So that's how here things are then in terms of this linear affine transformation theorem. We have this IN times epsilon plus x beta. And then from the linear affine transformation theorem, from before the break, we can read off the, we first know that the data is multivariate normally distributed. The expectation is given by the transformation of the expectation parameter plus our thing that we add to epsilon. So expectation of epsilon is 0n, transformation matrix is in, that's 0 because there are only zeros n there. And so we only have this x beta. So our expectation parameter of the data is x beta. And then if we sandwich multiply the covariance matrix here of the error with the identity matrix, again, the identity matrix doesn't do anything, then only the sigma square IN covariance matrix of the error remains. Yeah. So yes, the errors in the model are assumed to be Gaussian, and these are not errors in terms of residuals, right? So we haven't talked about residuals or estimating anything yet. So this is just the probabilistic model. The errors are assumed to be normally distributed. They are also assumed to be identically distributed and independently distributed. The data then are not independent anymore because there is some regularity that comes in here. But they are multivariate normally distributed and have as expectation the design matrix times beta. So I just said they are not independent, but they are independent because, sorry, I get a little bit ahead of myself. They are independent because they have a spherical covariance matrix, sorry. So the data points are independent, but they are not identically distributed because each of them has the value as expectation parameter that corresponds to the respective row in the vector that is given by x beta. And now, so that's kind of the general form. And now it's really then the time and also the task to see how different forms of x beta can encode different models that you all know, like, for example, independent Gaussians, t-test, ANOVA, simple linear regression, and so on. And actually both of them, so both the regression models and also the categorical models are important for fMRI analysis because typically on the first level, so meaning at the participant level, usually you use multiple linear regression. On the second level, you use categorical designs, and the specific designs we will look at tomorrow. Good, so that's the GLM, and we now look at two examples. The first being the model that's behind one sample t-test. That's the model of independent and identically distributed Gaussian random variables. And then we look at simple linear regression. And we will also look at them then once we have formulated the model. Again, this is all just model formulation for estimation and evaluation. So I somehow hope that you all remember the model for one sample t-test. There, the idea is that you have n data points, yi, which are realizations of a univariate Gaussian. So that's a univariate Gaussian here with the same expectation parameter and variance parameter. For psychologists and anyone, you might have always called these populations. Yeah, so this might be what you call the population parameter mu and the population parameter sigma square. That's often the case. I find it a little bit confusing to call this population because it always sounds like population. For me, a population is always some kind of finite thing. And then you can argue, oh, and we approximate it with, or we model that with an infinite thing and so on. But yeah, and it's also, it's getting a little bit tricky if you, it makes sense if you maybe think of heights of people and you sample the population of students or whatever. But if you think about, I don't know, EG signals or so on, and you apply a one sample t-test, yeah, you can also think about the population of EG measurements, but that's not a population that really exists. So then why talk about populations at all? But yeah, if you're familiar with the term, so these are the population parameters and everything here, that's all population level that we are talking about here, the beta parameters and the variance parameters. Here we now have the special case that all of the yi's have the same expectation parameter, and of course they also have the same variance parameter. We can write this based on what we have seen now with linear affine transformations. We can write this model, so which says that each data point is drawn from a univariate Gaussian with expectation parameter mu and variance parameter sigma, so all from the same. We can write this as that each data point results from the addition of an Gaussian error term or a univariate normally distributed error term centered on 0 to mu. Yeah, so that's the same thing that we did here in all generality, kind of backwards. Yeah, so instead of going from, okay, we assume that yi results from adding something deterministic to something random, we start with, okay, yi is distributed according to according to a univariate Gaussian, and we now write out that this is the same as adding a fixed mu to the random variable epsilon I, where these epsilon I are all independent and centered on 0, which is not a vector here because they're univariate. And this, again, we can write in matrix form if we define the following, and namely we define X as a column of ones, so only ones, and we define our beta, this beta here, now as that parameter mu, because then if we have this column of ones times mu, for each data point here, the mu's are the same. And then we have already cast now this model, which all of you know, as a GLM. Yeah. So again, so the important point here is that you all have seen independent, so n samples from a normal population. Yeah, you have seen that. Who hasn't seen n samples from a normal population? Or no, who has seen n samples from a normal population? You have. So who has heard about t-tests? Okay, then you have heard n samples from a normal distribution, because that's what you apply t-tests, at least the one sample t-test to. Of course, if you have two sample t-tests, then you have maybe, depending, yeah, then you can have two populations. But you all did one sample t-test or z-test, even easier when the variance is known. This is here, the variance is not known, so that's where you are. Now the point is that you can write this design, this probabilistic model of the one sample t-test, namely n independent and identically distributed Gaussian random variables as a special case of this equation here. And the special case means for x, you choose just a column of ones. Then it follows that if you have just a column, that your beta is only a scalar, and everything else is as it always is. So yeah. And then now your one sample t-test design or your independent and identically distributed Gaussian random variables become a special case of the GLM. And if that would be the only special case, then there would be no point. But of course, there are more special cases. And how one can work with that and how one can do things like estimating these parameters and doing t-tests, of course, this will follow in model estimation and evaluation. So here's a example in terms of doing this with NumPy. Here it's a little bit annoying that actually NumPy can't really deal with n/1 matrices that well. So here I actually have to use the standard multiplication operator, not the matrix multiplication operator. So it's not very nice. So maybe don't look at this too closely. Later for simple linear regression, it looks better. But here you can see that I defined beta as 2, the variance, so that's our mu then, the variance as 1, and then we want 12 samples, so we get 12 samples that here are roughly around 2. A little bit more exciting to formulate, but actually, and this is important, this design is important in second level fMRI analysis. Yeah? So the most basic second level, so group level fMRI analysis that you do is a one sample t-test design, which we will then again see tomorrow. And that's exactly this design. So it's kind of trivial, but it's also for group inference already very important. Not that important actually for fMRI analysis, but in general important is, of course, simple linear regression, which I guess all of you also have seen. So that's now a different model, but it has the same kind of structure and kind of the same format as we've seen previously. So simple linear regression, just first with a picture, that's this thing where you have some data and you somehow fit a line to it. Yeah? So where you have here the independent variable and here the dependent variable, and you somehow fit a line to it, whatever that means. From the perspective of the GLM, of course, simple linear regression is a special case. And let's first look at what we know about simple linear regression. So the ith data point in simple linear regression is modeled as an offset parameter A plus a slope parameter B times the value of the independent variable. Here it actually works quite well with the notions of independent variable because there's only one. If one looks at this, one also doesn't have the problem with the vectors. So here the xi would be the values of the independent variable, the yi would be the values of the dependent variable, and you have a slope parameter that scales the values of the independent variable, you add to it an offset parameter, and then under the GLM, you assume that there is additive Gaussian noise. You might have done ordinary least squares estimation in undergraduate statistics where you just fit a line and don't make this assumption about Gaussian error. That's perfectly fine. You can fit a line without assuming Gaussian error. You need Gaussian error if you then want to make inferences about the parameters in the classical setting. So if you, for example, evaluate a p-value for the offset parameter or for the slope parameter, then these p-values from the t-distribution, again, they don't come in if you not assume Gaussian errors in the beginning. So that's why they are here. And of course, they are also here because the GLM always assumes that. Now they are again mutually independent, and we can now state this model differently based on what we established essentially here, also here. So of course, this is the same here as saying each data point, each yi is distributed according to a univariate Gaussian with variance parameter sigma square and expectation parameter mu I, where mu I, again, is of course deterministically given by A plus B xi. Yeah. And then that's basically saying how the data points individually are distributed. But again, we want to cast this as a GLM. And to replicate essentially, or to express A plus BXI in terms of a matrix product, namely our X beta, we need to specify the design matrix as follows. We take a column of ones, and we take a column that holds the values of the independent variable, so the x's. And so then we have a design matrix with n columns and n rows and 2 columns. And our beta we define as A and B. Now, if we then multiply this, so going over rows, 1 times A, x1 times B, we get for y1 A plus B times x1. Then for y2, we get 1 times A plus x2 times B. So we have our x2 times B plus A. Yeah. So that's the design matrix form that, and the parameter form, of course, that encodes a simple linear regression design. And that's whenever you did a simple linear regression using R or whatever used in undergraduate statistics, or SPSS, if things were really bad, where you come from, then this was always what was happening in your program. So here, this is then kind of the proper way how you formulate the model, because here the expectation parameter for this multivariate normal distribution random number generator is the proper matrix product of X, which is a column of ones and a column of x's. And the covariance matrix parameter is just the identity matrix times sigma square. Then you here get these values out. Of course, it depends on your x's and what you use for beta. Beta is 1, 2 here, and your x's are linearly spaced between 0 and 5. And that's what's then plotted here. So there are, I think, 12 points. N is 12. Your x's are then 0, 0.5, 1, or not quite 1, yeah, so it's linear space between 0 and 5. And x beta, that's the expectation parameter. The entries are here then plotted as these white dots. And of course, because the x's are linearly spaced and you have a slope, the x beta I increases. But these are not your data point. Your data points are sampled from univariate Gaussians around this expectation. And you see sometimes the single sample here is below the x beta I, and sometimes it's above x beta I. I have for the psychology course, I have also a figure that shows kind of a univariate normal distribution, or the probability density function over this. It's quite nice to look at in a way, but it's also a little bit weird because it's not really color coded and so on. But that's the logic how to cast the probabilistic model of simple linear regression as a GLM. And again, the crucial thing is, so the formula, the overall formula always is the same. That's always this x beta plus epsilon. But now, of course, comparing one sample t-test and simple linear regression, the x and the beta and also their meanings have, of course, changed. So again, in one sample t-test designs, this is just a column of ones, and the beta is the expectation parameter that is the same for all of the Gaussian random variables. In simple linear regression, it's 2 columns, 1 column of ones, 1 column of values of the independent variable, and beta is also 2-dimensional vector, 1 value, the first value, or the one, let's say, that corresponds to the column of ones is the offset parameter, and the other parameter is the slope parameter. Good, so that's the formulation of the model. So what does that mean for data analysis? Not much, really, because that's just a probabilistic model which you can implement on a computer. You can sample And you can say, oh, the samples look a little bit like the actual one sample that I obtained in my experiment, but yeah, you cannot do much more than that because you don't know how to infer the parameters. Note again that the parameters here in the simulations, they are of course set. So the beta I define and the sigma square I define, and they of course refer to the true but unknown parameters that you have in any statistical model, right? So the population parameters in undergraduate statistics, they were always there, but you were only able to estimate them and you would never know them. Even if you estimate them, you don't know the population parameters or the true but unknown parameters, as I call them. So that's model formulation, and tomorrow morning we see how we can use this model to formulate a model for fMRI time series. But for this, we first need to then refresh our knowledge about fMRI time series. Other questions about model formulation right now? So is this really clear to everyone how to get simple linear regression out of there? Because I think you all know simple linear regression. And now I just shown you how you can cast that as a GLM. That's essentially what happened. Okay, so if that is roughly clear, that's good. So the trick, of course, and the knowledge that you need for that is, of course, how to do this matrix product, x times beta. It's kind of a nice matrix product in the sense that this beta is always just a column. So you always just get a column out and you don't need to, don't have like 30 entries in a 5x6 matrix and so on, but it's fairly straightforward. And of course, you need the multivariate Gaussian because this features as the expectation parameter of your multivariate Gaussian. Okay, that's the model formulation bit. And actually, if you do brain imaging data, just a second, if you do brain imaging data analysis, you will, when you create your design matrix, when you put your onsets into your program, this kind of X matrix is created. So you do model formulation anytime you analyze fMRI data. That was a question.
Are we going to cover repeated measures models?
No, to a certain degree. No, not really. So no, but we will discuss covariance component estimation, which is fairly related to repeated measures ANOVAs, but of course in a very different setting. There are different ways to do repeated measures stuff. One thing is to talk about the covariances. The other thing is how to specify a specific design matrices that refer to that. And then you can even go further and look at these things from a linear mixed models perspective. So where your betas then also become random variables. No, we're not going to do all of this. If you want to, so at this point, what we are talking about are between subject designs, if you want. Yeah. Of course, all of this can be integrated in the GLM program, is integrated, but it's more advanced. And with looking at covariance component estimation, we will actually look at one way of how repeated measures are encoded, where you don't assume that the data points and the errors are independent between units, but there is some form of covariation. Right now, that for example, yeah, here also, if you sample something lower than the mean here, it has no influence whether you sample something higher or lower here. In repeated measures designs, if you think this is the person on two conditions or something, and they have a specific bias, you would maybe assume that there is some dependency. You do that actually also in fMRI time series, where you use more than simple linear regression designs. And then you build in this covariation in terms of the errors into your model. So yes and no, that's what I can say. But repeated measures is a big topic also. Good, then I suggest we do a little bit more on model estimation, and then we take a break. So So far, we have just formulated the model, and as you saw in the simulation code that I showed you briefly, I specified parameters. And then if I have specified parameters, I can use my random number generator and sample data. Awesome, but that's not something that you do in data analysis. In data analysis, you have some data, so you don't need to sample something with a random number generator. You also only have one sample. But nobody has told you any parameters or something like that. And you want to then actually infer these parameters or make guesses about the parameters, the true but unknown population parameters based on your data. This is what model estimation is all about. Model estimation is kind of adapting the parameters to a specific data outcome. And one can, or one, and what we actually do in the summer term now in psychology, in the second term, is to, how we did it also a little bit in the first term, this is why we don't have to do everything, is to address model estimation from first a general perspective, namely, for example, introducing the principle of maximum likelihood, where you adapt the parameters such that the probability of your data becomes maximal. In regression designs, ordinary least squares estimation is also popular. Does anyone knows the intuition between ordinary least squares estimation? So the psychology people, kleinste Quadrate Schätzer. So what's the intuition there?
They just try to minimize like the errors of data points and line.
Yeah, exactly. Yeah. So overall data points, you try to minimize the squared deviation. And this is then an optimization problem for which there exist, at least in simple linear regression, explicit solutions. There you don't need to deal with the question of maximum likelihood, but one can quite easily show that ordinary least squares and maximum likelihood for the Gaussian are identical. This is actually by design. Because the Gaussian was designed to be kind of the distribution that is kind of maximum likelihood meist if you do ordinary least square estimation. But yeah, so you don't need to do kleinste Quadrate Schätzung ordinary least squares with probabilistic assumptions. Anyway, we are doing these things in the psychology courses, so to develop a more general idea of how to estimate parameters. Here, I will just tell you about the solution, essentially, and tell you that it's a good solution in terms of the expectation parameters. So first of all, what are the parameters that we need to estimate? There are p+1 parameters in a GLM. P, and by parameters I then mean individual numbers, so scalar numbers. Beta has p entries, so that depends. In the one sample t-test design, that was just a single number. In the simple linear regression, it was slope and offset. In multiple linear regression, in fMRI, it can be like 20 or so beta parameters, as they are then just called. So that's a parameter. That's a parameter vector with p parameters in there, and then there's the variance parameter. That's a single parameter, and both of them need to be estimated based on data. Now, one fundamental result in that's also called the Gauss-Markov theorem in the theory of linear models is that this thing here is an unbiased estimator of the true but unknown beta parameter. So what do we have here? We have the, and here again, I have the, so we have the GLM here, our n-dimensional data vector y, x beta, design matrix times beta, parameter vector plus epsilon, and epsilon again being distributed centered on 0, n, and with spherical covariance matrix, and here again, because it's copy-paste, the IN is missing. I hope I remember all the typos. Usually I put the typos in why I'm doing it, but I guess some of them I remember tonight, and then I adapt the things. So that's our GLM. And now this theorem here says that this thing here where we do the following. Essentially, we just multiply our data. So this is our data. And what do we multiply it with? The design matrix transpose. And we multiply this with the inverse of the design matrix product with itself. So here, transpose the design matrix, multiply it with itself, compute the inverse matrix of that, multiply it with the design matrix transpose, and multiply it with the data. That this operation here is an unbiased estimator of beta. What does unbiased mean? Unbiased means that the expected value of this estimator here corresponds to the true but unknown value. Why expected value? Well, this y is random, right? So we can create samples from our GLM and we get different samples for y. Now, if we have a different sample for y, our x, our design matrix, that's always fixed. Yeah, and then it's also fixed what this matrix product xt x minus 1 xt is. So we always multiply our different realizations of y with the same thing, but because the data when sampling from the GLM varies, also our beta hat here varies, and hence beta hat is also a random vector. One can actually also, and one needs essentially to determine its distribution. It's of course also Gaussian distributed because this is just again a linear transformation, linear fine, but it's in this case it's actually linear, hence, this is a random vector and we can think about its expected value. So we know its distribution, but we can also think about its expected value. And then one can quite easily show, if one is happy with expectations, that the expectation of beta hat is again better, because expectations only work on essentially random things. The only thing that is random here is y, and the expected value of y is of course the expectation parameter. In principle, one needs to show that, but that pertains to all Gaussian distributions, of course. And in principle, one needs to show that. Again, first semester psychology. And the expectation here is x beta, and then we have xtx minus 1 xtx, and then this is the inverse matrix of this, and we just get beta. The whole thing, and this is, so there are things that I'm not telling you here. Of course, the whole thing only works if we can actually compute the inverse of this matrix product here. That does not need to be the case, and that has to do with the fact of how dependent or collinear the columns of the design matrix are. If all the columns of your design matrix are identical, then this whole thing will not work. If there's no full collinearity, it will work, but it affects the variance of your beta parameter estimator. So there are some constraints. So the design matrix needs to be with a set of full column rank for this whole thing to work. But to explain that in detail, I would have to explain what rank is and so on. And we're not doing that. But for the mathematician and mathematicians, there are some constraints on the matrix X so that this whole thing works out. This is this form here, xtx minus 1 xt, that is the ordinary least squares estimator, and it's also the maximum likelihood estimator. So one can derive that under the principle of ordinary least squares estimation or under the principle of maximum likelihood estimation. We're not doing it now. So I'm just telling you, you multiply the data with this, and then you get an estimator. We can, however, think a little bit about what this is actually doing. So if you think about the design matrix and you transpose it, then you, of course, have, if you have like 3 conditions or something, then you have a 3 times n matrix that you multiply with the data. So you multiply each of your rows in xt, which is a column in x, with the data, and add that all up. So what you're doing there is essentially evaluating the covariance between the the columns of your design matrix, which become the rows of xt, and the data. And each of these covariances you then put into the corresponding entry in beta hat. Yeah, that's what this xt y is doing. And then you normalize that for the variability that is in x itself by dividing by this. One can do this in more detail. So if you are more into this, we will discuss this in some detail with respect to simple linear regression early on in the term. So 8th of April we are starting, and then there's Easter, but a week after anyway. So if you're more into understanding this solution rather than how it's derived, join us in the first 2 weeks of the summer term. But in brief, it's essentially with the beta parameter estimates, you evaluate the covariation between your columns of the design matrix, which are also called regressors, as I will tell you tomorrow, and the data, and then you normalize. So there is some intuitive understanding. But from a data analytical perspective, it's fairly straightforward. So if you want to compute beta hat, you use your inversion routine and you compute xt times x times xt times y, and then you have your parameter estimate. And you can use this formula for any GLM design that you have. So for ANOVA, ANCOVA, simple linear regression, multilinear regression, t-tests have you not for everything. Now, maybe before the break, and then we do 2 examples after the break. Yeah.
Can I raise a question?
Sure.
To the slide before?
Yeah.
I mean, I get the proof, but I don't know. Can you give an intuition why, or not an intuition, but why x inverse times y would not work as an estimator? Because when I look at 13, and we would multiply from the left-hand side x inverse.
Here.
Yeah, on both sides.
Yeah, so it's so that's kind of I see your point. So what you use here is a pseudo inverse instead of the inverse, and the point is that you don't have a solution to you. So the point is that you allow for an imperfect solution essentially. So you want so.
I just forgot that it's not usually n by n or whatever.
Yeah, exactly. So it's not a square matrix. So that's the first thing. So then there is no inverse whatsoever, and even then it might not exist. The other thing is that would of course mean that so in terms of simple linear regression, that you somehow, if you have the inverse, you would fit something that really fits. Although that doesn't all make quite sense, but what you are actually allowing for here in terms of this pseudo inverse of this not invertible matrix is to allow for an imperfect solution.
Okay. Yeah.
But a solution that fulfills other criteria, namely minimizing this sum of squares. But yeah, that's also usually, I haven't said that, but usually the design matrices have more rows than columns. So you usually have, because the multiple linear regression ones that we will look at, they have maybe your conditions in an fMRI experiment. Maybe you have 5 conditions or something, and then you have as many rows as you have data points for a single voxel. And then you have, for example, a 300 times 6 matrix or 5 matrix, and then you end up with this. Okay, so the other parameter, and before we look at examples for these estimators, the other parameter that you need to estimate is the variance parameter. And this turns out that can be estimated based on the residuals. So what are residuals? So if you have your beta parameter estimated, you have beta hat, then you can of course compute maybe we also have an example here. The prediction based on your estimate. Yeah. So what you see here now, again, for the simple linear regression design, you see the actually true but unknown expected values, or the expectation line here as before. You see the data points, and you see what you get if you have better had estimated. How that looks in more detail, we will see. But of course, there you have now two values for your offset and your slope parameters, so one for each. And you can also plot that. It's because the data is not quite as the expected value. You have a slight deviation here. And then based on this X beta hat, you can compute the difference between X beta hat I and yi. And this is, of course, also what you want to minimize in the first place. But of course, at one point you have it minimized, and then it still doesn't quite fit, as I showed you. And that's what's entering here then. So here you have X beta hat, and you subtract, you evaluate the remaining error after estimating beta. And then what you do here is that you square it and sum it all up. So you look actually at the sum of squares. So that's what's happening here in terms of this vector or the scalar or dot product. So here you have an n-dimensional vector. Here you have an n-dimensional vector. You get from the subtraction, you get an n-dimensional vector. You transpose it. You have a 1 times n matrix, and you have an n-dimensional vector. So you get a scalar out of that. Actually, each of these vectors here that you multiply, they are called residuals. And if you do the dot product of these vectors, that is called the residual sum of squares. That is a single number. And if you divide this residual sum of squares by n minus p, so the number of data points minus the number of parameters or columns of your design matrix, beta parameters, this works as an estimator for the variance parameter. And here again, you of course need the IN matrix. I always find that quite surprising somehow, that, but then I think it's also because everything is linear fine in this kind of setting, it makes some sense. If one derives estimators for the variance parameter under maximum likelihood, one doesn't actually end up here. The maximum likelihood estimator for the variance parameter is divided by n. That's the same thing that you all know from computing a sample variance, and you need to divide by n minus 1. That's the minus 1 there is actually the one column of your design matrix, if you want, in a one sample t-test design. And this, first of all, shows that you, or from this, you can, where am I now? From the maximum likelihood estimator, you can show that it's not unbiased, so its expected value doesn't conform to the true but unknown parameter value, but this subtracting minus 1 accounts for this bias, first term psychology. This estimator here is it's sometimes hard to find a name for it. Sometimes it's called ordinary least squares estimator. I prefer to call it the restricted maximum likelihood estimator. So a REML estimator, because there's a variant of maximum likelihood estimation called restricted maximum likelihood estimation, which is fairly prominent in brain imaging, and we will briefly see it tomorrow. Under that principle, you actually end up with this, although I've never shown that, but I know that this is the case. So that's then not the maximum likelihood estimator here, but the REML estimator, but it's unbiased. So again, the expected value of this estimator is the true but unknown parameter. And of course, you want to use unbiased estimators, because then you know if you apply them all the time to different data, overall you're doing a good thing. And again, once you have beta hat, this is straightforward to evaluate in terms of programming. And of course, you can always use the same formulas or the same programming code regardless of your design. So you subtract x beta hat from y, then you compute the dot product, RT times R, call it residual sum of squares, and then you divide by n minus p. Of course, you can do all of this in one step, but then my code would go too far to the right, and I don't like that. This is horrible here. Yeah. So this is kind of, these are the two estimators that one needs, and this is model estimation in the GLM. After the break, we will look at the examples of these estimators for the two examples that we have already seen, or at least one. Maybe just one, because the other one is a little more involved. Are there questions right now about these estimators?
N minus P is degrees of freedom, basically?
Yeah, so that's, yeah, so you can call it that. Yeah.
It would be equivalent to degrees of freedom, and like a.
Sure. It's yeah. I don't like the degrees of freedom things too much, because usually then what you use the degrees of freedom for is you use it for the t-distribution to look at which one you use. And there it's not actually the degrees of freedom, it's the parameter. So it's the degrees of freedom parameter. And then if you introduce S degrees of freedom, then it's easy to show that if you have n minus 1 and show that if you have the mean and 9 values, then the 10th is given. But to show that for higher p's, then that gets more involved. So that's why I try to avoid the degrees of freedom terminology most of the time. Okay, then let's have a break and continue, yeah, at 3, I guess. Yeah? Okay. And that, I guess, is then also the last break for today. Yeah, because we only have 1 hour left. So that's definitely the last break. Good. Good, then let's finish for today with first a brief example for model estimation and estimating parameters in a GLM, and then the important aspect of model evaluation. So again, the parameter estimators are always have always the same form for the GLM. It's always for beta hat. It's xt x minus 1 xt y, and for sigma square, it's always this residual sum of squares divided by n minus p. But of course, how these parameter estimators or estimates then look also depend on the design matrix. And so what I've included in the slides is explicit forms for the independent and identically distributed Gaussian random variables. So this one sample t-test design that we saw earlier on, and also for simple linear regression, but I will only discuss the Gaussian random variable one sample t-test design now. Yeah, you can look at the simple linear regression, but yeah, that's then also a little bit more interesting, actually, if you look at the relation between correlation and simple linear regression, then this also gets even more interesting if you look at the estimators in simple linear regression. And we're not doing this, so we're focusing now on this, but in the summer term in psychology in the beginning, will be there. So now we are again back to our one sample t-test design, where we have n independent random variables that are distributed according to univariate Gaussians with expectation parameter mu and variance parameter sigma square, which we cast as a GLM previously with this one column of ones and our beta being equal to mu. Again, this is sampling independently from a normal population. And then it turns out that our estimate for mu, which is our estimate mu equals beta, our estimate for beta or for mu, beta hat is just the mean, so the sample mean of our data points. And our estimate for the variance parameter is just the standard sample variance that you all know. And if you take the square root of that, of course, you have the sample standard deviation, which you might know even more. I don't know. How can one see that? Well, that's fairly straightforward. Of course, the beta hat estimator has this general form. Now, if our design matrix is just a column of ones, then this is, of course, the transpose column of ones times the column of ones. And so here you multiply 1 with 1 all the time, n times, and you add them all up. So you get n. And then you take the inverse of n, so the reciprocal, that's 1 over n, or n to the power of minus 1. And here you have the transpose of this column of ones, and you multiply all the data points with that. So you have all the data points, and you sum them all up. So here you have the sum of the data points, and then the beta hat is just the sample mean. No? So that's in the case of, just need to check. Oops. In the case of the beta estimator, so the unbiased estimate for mu is just the sample mean. That's also what you know since undergraduate statistics. And for the variance parameter estimate, it's fairly similar. Of course, you need to put in the things there. So X is your design matrix, a column of ones. Your beta parameter estimate is, as we just saw, your sample mean. And then what that means is that you subtract from each data point the sample mean, which I made explicit here. And then you square these terms here. So you multiply them with themselves, and then you sum them all up. That's what's then shown here. So yi minus the sample mean, and with the sample mean, of course, you often write the sample mean also as y bar, and then you're already done. So p is 1, so you have n minus 1. So these things that you of course know, and you might also know then that in simple linear regression there is this way that you can write the slope and offset parameter estimates in terms of the covariances and the variances, which also, of course, relates to this general understanding of the parameter estimates. This, of course, also reproduces under the GLM. It's a little bit more effort to show that, but it still can be done on a couple of slides. Okay, so that's then couple of slides. That's then with regards to estimation. So there are essentially two formulas. So far we've actually just seen 3 formulas. So y equals x beta plus epsilon, that's our GLM. And then we have the estimators, xtx minus 1 xty as our estimator for beta, for the parameter vector beta, and our residual sum of squares divided by n minus p as a estimator for the variance parameter. And this describes all the estimation theory for the GLM in the classical setting that you need. So you can now, in principle, estimate any GLM design. You just need to spell out the design matrix, and then you can estimate it. And that really makes things a lot easier than if you think about I don't know how you derive ANOVA and ANCOVA estimators in a classical setting, and then they may or may not be related with what you've seen before and so on. So now you have just 3 formulas and everything, and you can implement them and in computer, and they all work always if your design matrix is of full column rank. Now, that's just parameter estimation. And of course, one is interested in these parameters. Tomorrow we will see as the first thing in the morning that the sensitivity of a voxel to a specific experimental condition corresponds to its beta parameters. And yeah, in general, that's all one needs. But of course, there's also statistical inference, and it's not going away. And one wants to test hypothesis, or maybe not, I don't know. People have opinions about that, but they are being tested. I don't know. T values and P values exist, and so you might also be interested in knowing what those are. And then, of course, in terms of neuroimaging, if you have ever seen these kind of blobs on the brain with these yellow colors in terms of fMRI activations, these are, of course, then usually T maps or F maps sometimes, but most likely T maps. And so it makes some sense to talk about what one can do beyond parameter estimation with the GLM. And that's what model evaluation is all about. And then these things that you see in SPM tables, or the things that you report from an fMRI activation study, they of course also happen on the level of these kind of T and F statistics and P values. So as I said earlier, we only focus on T statistics and yeah, introduce them now in general for the GLM. And then tomorrow morning for creating beautiful brain activation maps. So what's, that's for the first time also correct. We start with the T statistic. What's the T statistic? So we start with the GLM. That's our GLM, yx beta plus epsilon, and epsilon is distributed according to a multivariate Gaussian centered on the zero vector and spherical covariance matrix. So it's the same thing all the time. And finally, the identity is also showing up. The other slides I need to correct. And we are considering our estimators, beta hat as defined previously, and sigma square hat as defined previously. Now, in addition, we think about a vector C, which is p-dimensional of contrast weights. For anyone who has done fMRI, these are the vectors that you always hack into SPM, like 1, 0, -1, 0, or something like that. So these are these contrast weight vectors. Sometimes they're just called contrast, but it makes sense to call them contrast weight vectors. And these you choose, so you can put there essentially what you want. The T statistic is then defined as follows. You compute the matrix product of this transposed p-dimensional vectors, so 1 times p vector with your p times 1 vector beta hat. So you get a scalar here. So this is 1 times p times 1, so you get a scalar. And you divide that by this expression here, so the square root of your variance parameter estimator times the contrast vector transpose times the inverse of your design matrix transpose times x times c. And also here you have a 1 times p vector. Here xtx is actually p times p dimensional, because that's an n times p matrix, but you transpose it, so you have p times n times p, so you have a p by p matrix, which is a square matrix, and you can compute the inverse. The inverse is again a p times p matrix, so you have 1 times p times p times p times p times 1. So you have a scalar also here, and then you divide a scalar by a scalar. Sigma square hat is of course also a scalar, and you get a single number. So what's happening there is that, of course, first of all, you now project your data, or you condense your data even more. So here you had p values in your beta parameter estimator and 1 value in your variance parameter estimator. And now you combine them. So you essentially divide the beta parameters by your variance parameter, but you, of course, project them onto a one-dimensional thing. So you end up with a single number. And then the question is, of course, what does this single number now mean? And as a first rule of thumb, it makes sense to think about T statistics as a ratio between an effect estimate and a sample size scaled data variability estimate. So essentially, t-values are always signal to noise ratios. So it not only telling you how strong your signal is in terms of your beta hat parameter estimate, but also how that relates to the residual variability or the noise in your data. When we look at that, maybe we do that here. Yeah, if we look at that for again the one sample t test design, then one can also make this a little bit more concrete. So here we have again the one sample t test design, and we now just saw that our beta hat parameter is the sample mean. So that's our y bar. And of course, our variance parameter is just our variance parameter. And now if we define C to be a p-dimensional vector, our p in the case here is just 1. And we define C to be just 1, so the number 1. And then, of course, we get in the numerator just the sample mean. And in the denominator, we get 1, 1, so that doesn't do anything. Here we have our design matrix inverse, so we get n to the power of -1. And we take the square root of these two things. So we get the sample standard deviation and divide it by the square root of n, which you also might know under the term standard error of the mean. It's the standard error of the mean. And yeah, we can also write it differently. We can also put the square root of n before that. And then we see that this general t statistic that we defined here, in the case of a one sample t-test design, with C defined as 1, is our standard t statistic that we know from one sample t-tests, namely the ratio between a sample mean and variance. You might be more familiar with t statistics from two sample t-tests, where you here have a difference between two sample means and you divide it by, for example, the pooled standard deviation. And you multiply accordingly with the different, so that's a little bit more tricky, with the two sample sizes. So what does that mean? So first of all, yeah, a t-statistic is here this ratio between the sample mean. So if the sample mean is large, then we get a large t-value. If the variance is also large, then the t-value, yeah, if they have the same size, is rather 1 or smaller than 1. Can also be negative, of course, if the sample mean is negative. This division by square root of n, which is of course the same thing as multiplying by square root of n, means that our t-value, or the t-value, is always getting larger the larger your sample size, which is also, yeah, something to take note of. So if you are interested in statistical significance, of course, you can get everything significant if you have a large enough sample size, because that's just how this thing works. And then, I don't know if you have heard about Cohen's d, which is kind of this effect size measure that psychologists love for whatever reason. That's defined as the sample mean divided by the sample standard deviation. And then, of course, your t-value is just the square root of n times Cohen's d. So Cohen's d and t-values can be just transformed into each other by multiplication or division by the square root of the sample size. So they're closely related. So if you there's not much addition. So this Cohen's d is essentially a sample size independent signal to noise ratio, or a t value is a sample size dependent signal to noise ratio. And you can discuss what you like more. Yeah, that's how a t value looks in the simplest scenario. Tomorrow we will look at t values that we then derive from our contrast that we usually see in fMRI, 1, -1, or 1, 0, these kind of things. Yeah. Now, the last thing then for today is that there are two things about the t-statistics. So I think t-statistics are fine. So there's completely no problem with t-statistics. They are signal to noise ratios. They represent in a single number the ratio between your estimated effect and your variability in the data. And of course, you believe more in your estimated effect if the variability is rather low. If there's a lot of variability as compared to your effect size, you believe it rather less. So there is no problem whatsoever with T statistics, and the same goes for F statistics. What sometimes people have a problem with is null hypothesis testing, although there's also not really a problem with null hypothesis testing, although maybe there is a problem with null hypothesis testing in the sense that it's simplifying things a little bit too much. The problem with null hypothesis testing is, of course, that you always say that you get a binary answer. So if you want to know about what hypothesis testing is, again, first semester psychology, of course, the outcome of a test is always a rejection of the null hypothesis, or not a rejection of the null hypothesis. So you have a lot of data, FMI data, whatever, and in the end you end up with a yes or no. And that's a little bit too simple for life, but nevertheless it's sometimes what people want. It makes sense, and I have no problem with hypothesis testing if you need to make a decision. Sometimes you need to make decisions, and then it's fine that you quantify uncertainty. You, in the end, still need to make a decision. And if you set up a framework that lets you do decisions in such a way that over many times, or maybe regarding your personal probabilities, subjective uncertainty, you make good decisions, that's good. If you don't need to decide anything, like in research, that is of basic research nature, where you just want to discuss with other humans what you think and what they think and what the data say, then I don't see much of a point of actually doing hypothesis testing. But if you need to make decisions based on something, then of course hypothesis testing makes sense. So that's a little bit on hypothesis testing in general. Hypothesis testing, we will not discuss that no, that's not quite true. Tomorrow we will talk about multiple testing, correction, and fMRI. So there's a little bit of hypothesis testing in there. Hypothesis testing, of course, always works using null distributions. So you all looked up the p-value for your t statistic value in the back of the book. And if this t statistic was larger than your critical value, or if your p-value was smaller than 0.05, you wrote, I reject the null hypothesis, or we reject the null hypothesis. And this, of course, is kind of interpreting observed data in the light of a null model. And this null model is basically the t distribution, or better, the fact that here the true but unknown beta parameter and your hypothesized beta parameter and your contrast give the same thing. So what do we have here? We have the GLM, and we have the t statistic almost. I call this here now the t-test statistic, because we subtract from t beta hat, we subtract ct, that's the same c, of course, a hypothesized parameter value, beta 0, that we can, of course, say is 0. So then we would call that the Nil hypothesis. So that's like assuming in a one sample setting that the true population mean is 0, but you know that that's not the only null hypothesis you can test. You can also test the null hypothesis that the true population mean is 2 or something, and that then would be a beta 0 of 2. If you consider this t-test statistic, and if your hypothesis parameter beta 0 is the same as your true but unknown beta parameter, then this t statistic, if the contrast of your hypothesis parameter and the contrast of your true but unknown beta parameter are the same, then this t statistic is distributed according to a student t distribution with n minus p degrees of freedom parameter. Yeah? In this case, it's t distributed. Why is it t distributed? Well, that's because one can justify that fairly simply. I didn't include this here. You find it in the script. If one has already established kind of the T statistic in general, and if one went from normally distributed data to Z-distributed data, chi-square distributed variance, and ratio of that. So there is quite a lot of transforming probability densities in between this multivariate Gaussian here and this T distribution, but it's an analytical result. Yeah. So if you start out with multivariate Gaussian data and you do these kind of transformations to it, then you end up with this distribution. Yeah, I don't really want to go into more details here.
One question regarding the C. This is something you pick arbitrarily, or
yeah.
Okay. So
if it's always 0, then it's so I guess there are some constraints on how we can choose.
It's like we hypothesize something about our data, and then we pick the C.
Yeah. So the C. It's a good question. So the C plays multiple roles, and we will also see them with fMRI data. So one thing is that we can use the C to single out specific parameter values. So if we define C to be just a vector of zeros with 1, 1, and we then multiply that with a beta parameter vector, we can look at a specific beta parameter value and see how this relates to the corresponding variance. What we can also do, and that's why it's called contrast, is that we can check, and this is actually what's happening in this example, is to see whether one parameter is larger than the other parameter, because if one parameter is larger than the other parameter, if we contrast this with a vector of 1 and -1, then if they are different, our difference is not 0. If they are the same, our difference is 0. So we can also, so essentially one can look at arbitrary linear combinations of beta parameter estimates. Usually one is interested in either getting one of the beta parameters or seeing whether there's evidence in the data to see that one beta parameter or say differently, to reject the null hypothesis that 2 beta parameters are the same using contrast. So I will show an example for that. How we use it in fMRI is very similar, and we will see that tomorrow. No?
Okay, so the other one was, if we say beta 1 and beta 2 are different, then we pick them as 1 and -1 and the rest is 0.
Yeah, for example, if there are more beta parameters. So here's a concrete example. I'm also explaining what this model evaluation wants to say. So this is now, okay, this is the identity matrix. This I get then from a slide further down the line, where we actually don't have the identity matrix anymore. So you can think of identity matrix here. It's actually also defined in the code as identity matrix. So what do we have here? We have a simple linear regression, GLM. So our X is n rows and 2 columns. We have 12 data points, and our X's are, again, so this is the example that we saw previously. That's this example. We now define true but unknown beta parameters to be the same, 2, 2, and variance to be 1. That's our model formulation. So that's what you see in the code, then just being written down up to here. And then we're looking at 3 different scenarios. I will tell you about them in a second. But what we also do is that we sample this model many times. And each time we sample this model with the true but unknown beta parameter and covariance matrix parameter, we compute the beta parameter estimator, the variance parameter estimator, and based on those, we compute the t value. Yeah? So we do that 10,000 times. So we take 10,000 12-dimensional vectors from the model, and based on the data y, compute the estimators and the t values. And then we collect all these t values and do a histogram analysis of the t values. Now, if the null hypothesis holds, and we will go into more detail about that in a second, then we can actually just reproduce, or we can show that using simulations that this actually is the case, that this t statistic is distributed according to students' t distribution. Here we have the probability density function of students' t distribution for the appropriate degrees of freedom parameter, and we have the histogram analysis of our t statistics. And as you see, and the histogram analysis normalized in such a way that it's a probability density estimate, so that's just about the scaling. And you see that indeed, if the scenario of the null hypothesis holds, then our analytical result, which is always the thing that we use to get p-values, can be reproduced using simulations. So that's hardcore or basic frequentist hypothesis testing and distributions of statistics in frequentist scenarios. Now, here you also see two cases where actually the distribution of the t statistics that are simulated is not the same as this null distribution. So let's have a look what's actually happening here. So the true but unknown parameter value is 2, 2. The beta 0 vector that is the null hypothesis parameter. So you might know that null and alternative hypotheses are spaces of parameter space that together make up the whole parameter space. And if one of the hypotheses has only a single element, like here, call that a simple hypothesis. So our beta 0 is actually our the vector that corresponds to our null hypothesis. We take it as 1, 1. So it's not the same as the true but unknown parameter vector. And we now look at different contrasts. One contrast vector 1, 0, one contrast vector 0, 1, and one looking at 1, minus 1. Now, if one thinks about what we have here in the denominator, our true but unknown beta parameter value is 2, 2. The beta hat estimators for that, of course, they will also be roughly around 2, 2. Of course, they will not be 2, 2 because it varies, but the expected values, so over many iterations, the mean will also be 2, 2. Now, if we compute these contrasts here with 1, 0, we get the first element of beta hat, and here this we can do explicitly without anything. So that's 1, 0 times 1, 1, and then we get, of course, here 1. Now, this statement says that if these contrasts, so CT beta hat and CT beta 0, if they are identical, then the t distribution, then the t statistic is distributed according to students' t distribution. If this is not the case, this may not be the case. And this is what's then happening here. So in the first scenario, our estimates will always be, and our first estimate here will always vary around 2. As you can see here, but our and we tested against the against this contrast value of 1, and then we always have 2 minus 1, so we get t values here around 1. Actually, you see the 1 here, not the 2. What does that mean? That means that our hypothesis here is not what's actually happening. The true but unknown parameter value is not what's is not 1, but it's 2. So from a hypothesis testing and getting great results, this is actually a scenario where you would get great results. You could even test the hypothesis, of course, that you have zeros here, so no effect. If this would be no effect, then you would even get higher t-values because your true but unknown beta parameters are, of course, not 0. So your null hypothesis is wrong which you know here from the simulation, and hence your t-statistics are actually not distributed according to the null distribution, but you get higher t-statistics all the time. They have actually, what they have is a non-central t-distribution, and one can also, one could also show that here you need non-central t-distributions for power calculations. So that's why non-central t-distributions are something quite normal. Here, then for the second contrast, it's similar with the difference that it's here, of course, looks much more pronounced, namely, which has to do with the fact that here, of course, the first and the second parameter enter quite differently. One of them is the offset parameter, the other one is the slope parameter. So also the entries in the design matrix play a role, as far as I thought about it. Yeah.
Yes. Maybe I'm confused, but the t-statistic is for the whole model and not for a single parameter. For both parameters.
Yes, but depending on C, you of course focus on one or the other.
When one is 0, it's just one.
Yeah, it's just focusing on that. So it's doing the C. Has anyone entered ones and minus zeros into SPM? No, but you're all interested in FMR. You have done that. Okay, so that's what these C's are about. The typical thing that you enter in SPM or for fMRI is this 1 minus 1, where you want to see is there a difference between the true but unknown parameters. And here we now have the scenario that, of course, the true but unknown parameters are the same. And you want to test the null hypothesis that they are the same. And the alternative hypothesis, of course, that one of them is larger than the other one. And what you can then see here is that it's actually, in terms of your hypothesis parameter, it's not the hypothesis parameter that really matters. What matters is the contrast of your hypothesis parameter compared to your true but unknown contrast beta parameter or true but unknown values. Because here, our contrast value is 1 minus 1. Our hypothesis parameter is 1, 1. This is, of course, qualitatively the same as 2, 2, but it's not the same value. Also should have a t here. So it says both of them are the same. If you do the contrast with this, you get 0, and here you also have that. So the null hypothesis that they are the same, that the difference is 0, is true. And this is why here in the last scenario, the t-statistics actually follow the null distribution because that's the case. It's not that one of the beta parameters is larger than the other beta parameter. In fMRI, this then would be a null result, as we will see tomorrow morning, because it means that your voxel is equally responsive to both conditions, as we will see tomorrow. Yep. Yeah, it's a good question. I also didn't go into many more details, but the difference is, of course, how the columns of the design matrix look, and how then also the denominator, so then nana, is different. Because you select, if you do xtx, then of course that's the same, but on the ones at one point of course, if you do x, and if you have this first column of ones and the second column being something different, then on this you have n. And here, of course, depends on. Here it doesn't depend. Here you have the sum of the xi. Here you also have the sum of the xi, and here you have the sum of the xi squared, right? Now, if you multiply this with 1, 0 and 1, 0, you get n. But if you multiply that with 0, 1 and 0, 1, you're actually extracting this value. Yeah?
Okay.
and this enters in the denominator. So the denominator is different. The numerator is the same, but the denominators are different. So that has, intuitively, this is about the variance of your independent variable here. And yeah, I think one can even think more about that, why you get larger values then and not smaller values. But that at one point, I think.
So, if I understand the first one,
Mhm.
and now we are using three different contrast rates to see how which one offers better.
Sorry?
Which one offers t statistic?
Yeah.
So, which one of these three is like desirable for us?
Yeah, that depends a little bit. So, so it depends definitely on the interpretation of your beta parameters, which always change between different models. For example, in this setting, this contrast. So to say the slope parameter is larger than the offset parameter, or the offset parameter is larger than the slope parameter, is kind of irrelevant. So I don't know. So you do a simple linear regression, and then you say, okay, the slope here is more than the offset. That's, I don't know, it doesn't really have meaning. In terms of the one sample t-test design, you can say, okay, our population parameter, we have evidence in the data that speaks against the null hypothesis that our population parameter is, for example, 0 or 2 or something like that. So there it makes a little bit more sense. The most sense it then makes in terms of this contrast, sorry, in terms of this 1 minus 1 vector, if you have beta parameters that somehow relate to the same thing, and tomorrow we will see that if you have two conditions and each of them is then in terms of its effect size encoded in one beta parameter, then you can, of course, using this 1 minus 1 contrast, see if a certain data set is more responsive to one or the other conditions, and that's something that you want to use in fMRI. So it's actually, yeah. So it's not usually what people then look, for example, in simple linear regression is that they in simple linear regression, I think the typical thing would be to say, okay, the slope is different from 0, so that you look at this contrast here to say, okay, there's the dependent variable varies in a non-zero fashion from the dependent variable co-varies with the independent variable, so you have a linear relation between them. And you can, of course, and that's then what I'm not doing here, you can translate this into their correlation is not 0, so that you can, that's again what's happening in April in psychology. So in this scenario, I think what would be of interest would only be this contrast. This is fairly meaningless, and this you can, yeah, if you want to say something about the slope, so what you get if your independent variable is 0, so what's kind of the offset, and you want to make a claim that this is not 0, so people at baseline, whatever they actually mean, already express something, then this might also be a contrast of interest.
But we already have like a hypothesis parameter beta naught.
Yeah, so you have to do.
So is it advised, like, should we go for, is it so that if we take more number of C's, then we will have a better chance to, like, is it something like that?
No.
So we can take any number of C's. Why did we take 3 C's?
Yeah, that was just because I wanted a figure with 3 plots. Okay. And I wanted to kind of spell out a little bit that it's not so much the beta 0 value, but the contrast value. In principle, what you do here, and if you would actually do hypothesis tests now, which I of course don't spell out, as soon as you compute more contrast, you actually have a multiple testing issue, and you might want to control, if you're actually doing this, using this for hypothesis testing, account for the fact that you do some multiple testing. Interestingly, in fMRI, you control multiple testing, but over voxels and not over contrast. People are happy to evaluate all sorts of contrast and report all of them and not account for that they're doing multiple testing there, or multiple comparisons, as it actually could be called there. But they account for the fact that they're doing that over many voxels, as we will see tomorrow. Okay, so that was what I wanted to do today. So we formulated the GLM, saw the parameter things, and model evaluation is then always there. One actually has to start thinking. So in a way, model formulation, model estimation is always the same set of equations. But then if one makes it concrete, one of course needs to think about what do my betas mean? And we will think about that all morning tomorrow for fMRI. What do my betas mean? And then if you know what your betas mean, then you also get a feeling of what your t-statistics mean. That, of course, varies from scenario to scenario. Yeah. Okay, so I'm done. Are there any more questions right now? No. Yeah, in terms of practical aspects, so you have also the all of this code that generates these things available. So the way I deal with that is sleep enough, get up, drink a coffee, sit down and write down the code and see that it's doing the things, and then you get more into that. So yeah, kind of use these resources. Tomorrow, if I, because we will also see some fMRI nylon simulations tomorrow, I will bring my other laptop, and then I can show you a little bit also how this is happening in Spider, but how this is looking. But then it's like, if the code is there and it runs, then not much is happening. It's just a figure popping up. So, but we will, yeah, I think, see a little bit more code that is also doing a little bit more interesting things tomorrow. But then I also firmly believe that you need the theory, and because otherwise you just do something and you don't know what you're doing. So enjoy the theory while you can. Good, then let's stop here and reconvene tomorrow at 9 o'clock and look at the GLM for fMRI tomorrow, now that we know what the GLM is. Goodbye.